So it is a big difference between statistical average and quantum theory. But the mathematical part, what you presented, was absolutely correct. Just interpretation was a help us to connect counterintuitive to simple things. Want to argue? Back?
I wouldn't argue against
Good.
that.
Then we'll continue discussion later. More questions? If no, let's thank the speaker and continue our intense schedule with Christian news and very important postulate number 5 about how the observer changes the system.
Yes, I know I said my name only. He's also part of the group.
So we had postulate number 5.
Yes.
The main thing we took from this is by measuring or observing a system, you can effectively alter it. Crude analogy I liked was checking like your pressure in a tire. You keep reading, but in doing so you let some of that air out, so you've affected the state of that. Now in physics, this is known as the observer effect. In a lot of the situations, it's negligible and doesn't need to be accounted for, but when on a quantum scale, you need to account for that, and it can be substantial. This idea is kind of explained in the thought experiment of Schrodinger's cat, and was even studied in an experiment done at the Weizmann Institute.
So going off what he said, the thought experiment that probably all of us know is the Schrodinger's cat thought experiment. Schrodinger, the way of explaining this, decided to put in his thought experiment a cat into a box. In this box, there's a vial of poison that at some random moment in time, we don't know because you close the box, the vial will open and kill the cat. Well, because the box is closed and we cannot see the cat is both alive and dead at the same time. So, now the question is how is this similar to electrons in the fact that it is both a wave and a particle at the same time? So then we have the Weizmann experiment that goes through and does this experimentally in real life. What the institute did is that they took a current and ran it through a double slit, and on this double slit area, they put some type of device that was able to observe what is going on. Now, when they started observing, the current going through did not. The more they observed, the less interference that was happening, and it ended up forming into particles. As you can see right here, as the more observance increases, the more that happens. But as they decreased the device observing the current, you see interference growing, showing that as you observe, it becomes more of a wave than a particle.
So like looking at the Weizmann experiment, if you're wanting to observe the system electron when it's acting as a wave, after observing it, you force it to act as a particle. So if you're doing measurements after that, it's a different state. So to get back to the wave, you're going to need to manipulate it back to the original system to do your measurements. And that was a thing, but when you're doing subsequent measurements, you need to make sure that you manipulate the system back to its original state.
Okay, thanks the team. And it is time for questions or comments or expressions of happiness. I have an expression of happiness. They really very comprehensive. I learned a lot. So, and it is good pedagogical step to say that first, for interference, for superposition, you look on the wave nature, but at the measurement, you look on it as a particle nature, and you observe this change of the state, right? Mm-hmm. I cannot design question, I cannot comment. So, in previous talks, maybe number 1, last slide in number 1 was a superposition. Summation, eigenfunctions with different expansion coefficients. So, the measurement breaks superposition and projects system onto one of the eigenstates. So it is I was trying to say what they were telling in more standard way. But they did in a very nice illustrative way. Last chance for other questions. If not, let's thank the team once again. We are a little behind schedule, but we still have chances to finish in time. Postulate number 6 by Andrew Olson and Braden White. Wait, like heavyweight. Okay. So something about time dependence.
All right, so we got postulate number 6, which is kind of generally stated as the time-dependent Schrodinger wave equation, which is kind of a general thing. So what we wanted to do is give a better interpretation of maybe a solution or the different parts that would make up the time-dependent wave equation. So we kind of did this first slide kind of in class the other day. You have your time-dependent wave equation on the top, which would be a linear first order partial differential equation. And then you can make some substitutions, assuming that the time portion is independent of the spatial coordinate portions. And you can guess the solution to be something as such. And you can reduce it then to a linear second order ordinary differential equation, which is much simpler to solve, especially in relatively easy cases.
All right, so what we're going to get into is what is H hat. It's essentially the sum of the kinetic and potential energy, T being the kinetic and V being the potential. So T is generally similar across all systems, so it's given by that equation. V, however, differs in like big situations. For classical, we have gravity, the standard gravity equation, and the spring equation. And then quantum, we have a slightly different equation. I'm gonna get into that a little bit.
Well, so gravity, we all know MGH, right? Just an example of a potential that we all know. But more specifically, we can talk about the spring, right? So it has this effective rigidity constant K, you can call it. And if you remember what that is, K is equivalent to the square root, or it's related to the frequency of the oscillation between the spring, right, and the mass. So it's actually equivalent to, say, K and omega squared if you make substitutions for mass as well. So we write it this way because in quantum mechanics we look at more of the wave-like nature rather than the simple rigidity. And that happens in a lot of the potentials that we look at. And to tie this all back into the time-dependent equation, you can solve these using the potential V and the potential T as that the second order ordinary differential equation. And so then the time portion just comes in at the end as that exponential factor relating the energy, which is encapsulated within that lambda I have shown. That's pretty much.
Okay, let's thank Braden and Andrew. I promise to learn all names by the end of the semester. So, questions? I definitely have some. So, in the previous slide, last equation to the left.
The EX.
Yes. How general it is. So, let me prepare a question and I will declare what I mean. We are trying to stay away from practical applications for a couple of meetings and try to declare very general statements that will work for universally for any system. And I have a suspicion that first two lines are general, but here, instead of using Hamiltonian operator, Braden and Andrew replaced it by the second derivative. And the suspicion is that maybe it's not general enough and it deals only with one particular case study.
The free electron.
were. Yes. So everyone, if you do not see sparks in the eyes, you need to repeat it in different words.
So the way this is written, to make it more general, to incorporate any general potential, like I did on the following, where I took different arguments of V, I simplified it, and there should be a dx squared here in parentheses, along with some arbitrary potential operator with a coefficient in front of it, because I created this E argument, so there should be the second derivative plus some coefficient, which would be similar to E minus the eigenvalue.
Okay. So, but it's still with this generalization, it will be their conclusion that it will be linear second order equation is correct. One more question, if no other questions. Would you agree that this equation can be characterized as eigenvalue problem? Good, thank you. Nice one. Let's thank you. So, and we have last but not least presentation by Jan Berg and Mark Elmland. So we are done with postulates of quantum mechanics, but we need to refresh. You can come up and set up your slides. But after we agree with these background postulates and before we go to applications, we need to be sure that we have enough mathematical muscles. And you have observed from the slides, for example, from last slide, last equation, that we need to solve eigenvalue problem. And from the first and second postulates and answers on the question, that from time to time we need to apply operator to the wave function. Two procedures: eigenvalue problem and apply operator to a function. This is very closely related to our Babbage from the taken, not only calculus, but also linear algebra. And these two operators, multiplying operator by a wave function, which is translated into matrix by vector, and then the eigenvalue problem will be illustrated by Jan and Mark. The floor is yours.
Before we get into the actual eigenvalue stuff, multiplying two vectors together, we have the cross product, which is done by taking the one of the rows and then multiplying it by the square that's left over to eliminate an item's row and column. And then you take the determinant of that leftover square, and then so you get I plus I times BF minus C, and you take that for I and J and K, and you get your cross product.
Can you ask the class if everyone is happy with concept of determinant?
Does everyone understand the determinant? That's kind of what I was trying to explain. So the determinant is for 2 by 2, you multiply the BF and then you subtract the EC. And then so with a 3 by 3 determinant, you can take the top row, so the I times the determinant for the bottom right hand corner, and then for J you would take AF minus DC, and then K you would take AE minus DB over here, and that would give you a vector as a result. So that's everyone gets that. And then skip over diagonalization because he'll actually cover that with what we actually care about. And then for multiplying matrices, I actually didn't get this slide in on time for the handout, but the slide before it for multiplying matrices can still be applied. You need a 1x3, so rows by columns, and then you need to have the columns of the first one times the rows of the second one match up. And then so you can multiply by the first row by the first column, and then the second row by the second column. However, what we're concerned with is multiplying vectors. This would also be called the dot product. You just multiply them in a row and you get a scalar result, or a 1x1 matrix. And then that's all I've got.
Okay. And I'm not super fancy, I don't know how to work computers, so I just wrote things, so I'm going to point up. So, eigenvalues, basically how you determine your eigenvalues from your operators is you want to take the determinant of your operator and set it equal to 0, right? So it's your determinant of actually your eigenvalue times the identity matrix, right? Minus your operator, set that equal to 0, if that's what this is. So that's your eigenvalue times your, keep forgetting what that's called, identity matrix. It's that one. Minus A equals 0. So then your determinant would end up being lambda minus A times B, and then B, C, lambda minus D. So then your determinant is going to come out to be a quadratic equation for the 2x2 matrices, right? And you just solve for your eigenvalues, and that's how you end up with your eigenvalues. I don't have anything written for eigenvectors, but basically, can I write on this? No, I can't. Okay.
You should be able. You should be able. Let's try.
Oh, bottom left.
Oh, nice.
Yeah. Point. Select this pen when it pops up.
Okay. Nope.
No, when it pops up, you need to select the pen.
Which pen? There's 2 of them.
This one. Select.
Oh, see, that makes a lot of sense. Thank you. Okay. So then for an eigenvector, basically we just found the eigenvalue. It's right here. So for the eigenvector, if you want to find that, it's basically you take your, I'm just going like this. A times lambda equals your lambda v, right? So you're trying to find your vector right here. Then you would plug in your eigenvalue and multiply that by your vector, and then you kind of work it through.
You want AV times lambda v, right?
Good.
Oh, thank you. AV times lambda v. Get rid of that. That makes more sense. So then you take your eigenvalue down here and multiply that by your vector, so you can just put that into your v over here and then multiply it through.
Okay, and solve it as system of linear equations.
Yes. So then I can't see my thing, dude. So you would end up writing out your A and then solving for your V if your V is V1, V2 equals these. So like your A's. So you would write out this system of linear equations and then put your value for lambda that you found into your V over here. Right?
Keep going, we are short in time.
Well, I think that's all I had.
Okay, let's thank the speakers. And the questions to the speakers. To Jan and Mark. I was not looking into the class and I didn't notice were there sparks in the eyes by the word of determinant. So therefore, can you guys tell what is determinant and who needs it? Give a definition, not mathematical definition, but for like common citizen.
Well, the determinant is the, isn't it like a matrix times, no, it's not a matrix times a null space, but a determinant is.
It is a procedure that converts matrix into one number.
Okay, that works.
Objections? Okay, and there are some specific rules how to make it. Even without this diagonalization and eigenvalues, it is a way to judge if a matrix is a good matrix or bad matrix. Some of you, I mean you too. So this gentleman were offering pseudo diagonalization, simplified diagonalization by swapping rows and columns. But such tricks work only if the determinant is not equal to 0. So if the matrix is non-singular. So determinant is a quality control of a matrix.
If it's invertible, you can do that.
Yep. And in the advanced chapters of linear algebra, one uses it for finding these eigenvalues. It is a background from linear algebra that we definitely will be using in the course. So ask them now after the class, refresh your memories about diagonalization. It is something that you will definitely need. Let's thank speakers once again. Many thanks to all presenters. And from now on, you are certified experts in postulates in quantum mechanics. Looking forward to see you Monday 11 at this place.